Today we are going to continue on in chapter 14. So last week we started into it, we're talking about mixtures and solutions, talked about some different types of solutions, mixtures and things like that. But really what we spent most of the time talking about was calculating concentration. And if you remember, the most important one that we are going to use the most is called molarity. That's how many moles of whatever substance you have that are dissolved in 1 liter of your solution. It's very, very useful because you can go directly from a volume, you can measure out a volume of a solution in the lab, and that will tell you how many moles of whatever it is you're working with there. So today we're going to talk a little bit more about mixtures, obviously, but we're going to a little bit more about like the process of making, like what actually happens when you dissolve salt. Okay. And that process is called solvation. That just means you're taking something solid, and you're mixing it in with you're dissolving it. Yeah. Those are the words we're looking for. So, now, most of the time, when we dissolve something, it's going to be that we're dissolving it in water. It's not every single time, but most of the time. Okay? And so, unless we say differently, we're going to say we're dissolving in water. So, now, keeping with this, concept of dissolving salt. Now, salt is an ionic compound, and of course, in chemistry, salt can mean a lot of different things. So we'll go with just the standard table salt, sodium chloride. So when this dissolves, okay, so remember, we're actually building these big crystals. And as it dissolves, all it does is, well, this chlorine ion over here is just going to leave. Okay. Now it is negatively charged, it is an ion. And in order to make that dissolve, well, remember water, if you look at our water molecule here, we have the negative charge there, the positive charge on both of those. Okay. So this chlorine ion is negative. Now the negatives don't want to be next to each other, but the positives really want to be next to the negative. So what actually ends up happening is it ends up being surrounded by a whole bunch of positive hydrogens. And that's why it can dissolve, because it can be held in that little pocket right there. Now, if we take off this sodium ion, it's going to be just the opposite. Okay? Sodium is going to be positive, which means the water molecules flip. And it can be more than 3. I'm just, in fact, it often is more than 3. I just am only drawing 3. So that's basically what happens when we have some sort of solvation of an ionic compound. Now, most ionic compounds will dissolve in water. Not all of them. An ionic compound that wouldn't dissolve in water, basically, the reason why it wouldn't is that the interactions here are stronger than these interactions. These interactions have to physically pull it apart because they would rather be like that. It's a stronger interaction. But most ionic compounds can be pulled apart because water has that positive and negative. So. Now, obviously, not everything that dissolves in water is an ionic compound. Probably the best example is sugar. Now, sugar is a big molecule. The sucrose that you would use, if you were putting it in a drink, is actually C12H. Oh goodness, I forget which one it is. Let's say it's either 23 or 24. I think it's only 23. It's gonna bug me now. I have to look it up. Okay. So that's a lot. Okay? It's not just going to be surrounded by a couple of water molecules. And there's no obvious charges on that. If we break off this sodium, well, it's a positive ion. Okay? The reason why sucrose dissolves in water is because a lot of these are in OH groups, hydroxyl groups, that's what we call it. This forms a polar bond, just like we see right here. Okay? And since it has OH groups all around the outside, those OH groups can form hydrogen bonds, just like the hydrogen bonds between water. If it was not able to form those bonds, those hydrogen bonds, well, it wouldn't dissolve. Okay? There's a rule that we follow, and it says like dissolves like, which basically means if it has polar properties, it can be dissolved by a polar solvent. If, however, it's nonpolar, it's going to dissolve in a nonpolar solvent. Now, sometimes we can find solvents that are both polar and nonpolar, depending on what part of it you're looking at. So they can dissolve both, but often it's a trade-off because it won't do any of them as good as if it were fully one or the other.
How would acids work?
So acids, we're going to get into acids and bases here in a little bit, but basically acids are things that, well, this is a simplistic view. This is basically where we started with acids. It's not the best view of acids, but basically acids can form what they call, well, it releases a proton, and then that means, so we have, so this is our acid, whatever type, plus a proton. We mix it with water. We get the H plus that comes off, okay? And you get the A minus. And so those have the charges kind of like the ions. So, and that'll make more sense when we talk, I think it's chapter 17, acids and bases. 17 is equilibrium, I think it's 18 then. Yeah. So, but yeah, it's very similar to this process. The proton breaks off, and then yeah. But yeah, so we have this. It's polar. It's polar. It can dissolve in polar solvents. It's nonpolar. It dissolves in nonpolar solvents. Obviously, there's energy released and things like that. Anytime you're moving bonds, there's energy. Depending on what is broken and what is formed, sometimes dissolving something makes things cool down. Other times, it makes things heat up. It just kind of depends what you're dissolving. In different energy states. We haven't done too much with energy. Chapters 15 and 16 are where we get to deal with energy. So that's, sort of the basics of what is going on. Okay. We're going to talk a little bit more about it, obviously. We want to talk about things that affect how fast this process happens. Okay? And we have 3 different factors. Call it agitation, surface area, and temperature. Now, agitation, basically it's a science word for stirring. Okay? If you take sugar, put it in your drink, you stir it, it's going to dissolve faster. Okay? Or if you shake it or whatever. Okay? If you just let it sit there, yeah, eventually it's going to dissolve, but it's going to take a lot longer. Surface area. So if we have one big chunk versus that same mass in a bunch of small chunks, okay, the smaller ones are going to dissolve faster. The reason for that is more surface area. Okay? Solvation can only happen at the surface of whatever you're dissolving. So if you have a bunch of little pieces, that increases the surface area dramatically, and it dissolves faster. And then temperature. Hot things dissolve faster. Basically, there's more energy moving all of these pieces around, these molecules. In order to break a piece off, the molecules have to bump into it. And if they're moving faster, we can get more bumping in. That's really, yeah. So, okay. Now the book talks about saturated and unsaturated solutions. So basically what that is, so let's go back to our dissolving salt, okay? Now, you put a bunch of salt in water, it dissolves, okay? You put more in, it dissolves. You put more in, it dissolves, okay? Eventually, you're going to reach a point where no more will be able to be dissolved. And remember, we have, we have to be able to surround these ions with water. Okay? Well, eventually, there's not going to be any more water molecules in order to pull that salt. Okay? The point at which it can't hold anymore, we say that is a saturated solution. Okay? It cannot hold anymore. If it's below that point, we call it unsaturated. It means it can continue to hold more. Okay? But here's the thing. Different temperatures have different saturation amounts. So if you take that same salt, so you've added salt until it's no longer able to dissolve anymore. Well, if we heat it up, we can get a little bit more. Okay? Now, usually, if you look at the graph on page 493, you can see that there is an exception to the rule. Cesium sulfite goes the opposite, but just about always, if you heat it up, you can get more. How much more depends on your substance that you're dissolving. So, but the point of saturation does change depending on temperature. Of course, what if we heat up that solution and we dissolve a whole bunch more? Okay, so now salt, if you looked at the graph, it doesn't really get a whole bunch more, but sugar does. So if you heat up sugar, if you heat up the water that you're dissolving sugar, you can dissolve a whole lot more in it. Well, what happens when you cool that back down? Okay. Well, technically, now you have more sugar than should be in that solution. We call that supersaturated. It's above the saturation point for that temperature. And as long as it cools slowly in a very, very clean container, it will stay supersaturated. But if you shock the system, or even if you just add a little tiny piece, what we call a seed crystal, whatever it is you've dissolved, all of a sudden it's going to start coming out of solution. And now you can do this with, this is how we make rock candy, if you've ever done that. You boil water, dissolve a whole bunch of sugar in there, and cool it off, and you put like a stick or a piece of string or something, and that sugar comes out of solution because it was a super saturated solution, forms big sugar crystals that you pull out and eat. Okay? Rock candy is literally just a bunch of sugar. So, anyway, so now book talks about the solubility of gases, and obviously you can dissolve gases in liquids. If you've ever had soda, and that's a gas dissolved in a liquid, in carbon dioxide. Okay. Um, the the amount of gas that you can dissolve in a liquid depends on how much pressure it's under. Um, Basically, the more pressure, the more you can dissolve. Okay. And that makes sense. Like if you think about it, when you open up a soda, you hear that release of pressure, and all of a sudden a whole bunch of bubbles start coming out. Um, that that is what we call Henry's law. Okay? Once you release the pressure, the bubbles, the gas that was dissolved in the liquid is now coming out because there's less pressure. Okay? It's pretty straightforward. There is Henry's law. It's in the book, but I don't give you any homework on it, so we're not going to go through that. But it's pretty straightforward. It's exactly like a lot of the gas laws. You'll get three of the values, solve for the last one. But once again, pretty sure I did not give you any of those on the homework because we've done a lot of that lately. So instead, we want to shift our focus to section 4, which is called colligative properties of solutions. Okay. So colligative properties, it doesn't matter what you've dissolved. It doesn't matter what you've dissolved, it just matters how much. Okay. It just matters how much. Now, it talks about things called electrolytes, which are basically when you dissolve ionic compounds. Okay. Ionic compounds, if you dissolve them in water, you get those electrolytes, which, well, they're called electrolytes because they conduct electricity. Okay. If you have absolutely pure water, it's actually a very, very poor conductor of electricity. But as soon as you put some salt in there and other electrolytes, all of a sudden it's a great conductor of electricity. Okay? Those electrons are going to start flying, but only because of the electrolytes in there. Okay? And the more electrolytes, the better it's going to move. Okay? Just put a little bit, well, you'll get some electricity, but as you put more and more, it becomes a better conductor. So, it talks about vapor pressure. We're going to skip that. I'm more interested in talking about boiling point elevation and freezing point depression. Okay. So dissolving something in water is going to change the temperature at which it boils and the temperature at which it freezes. Now, that as we talk about it, you've probably experienced these things already in life. Okay, but anyway, so the book first goes into boiling point elevation. Okay. Now, obviously, there's math associated with this. Okay. It's not too bad though. Our equation so let's break down this first part here. T is temperature, okay? The little b means it's the temperature of boiling. This triangle is actually a Greek letter. It means delta, and it means the change. Okay, the change. And then we have K sub B. This is a constant, but it's a constant for the solvent. Okay, remember, it doesn't matter what we're dissolving, it just matters how much. Okay, so water has its own K sub B. Every other solvent out there has a unique K sub B. Okay. You can see some of them on the chart, page 500. Okay. For water, K sub B is 0.512. And then we multiply that by little m, which remember is molality. Okay, so this is one time when we will use molality. So that's just, but when you add salt to water, it's going to increase the boiling point. It's going to have to get hotter to boil. Now, it's not a ton. That's a pretty small K sub B, but it is. Going the other direction, freezing, we call it freezing point depression because it lowers it. Okay? And our equation is almost identical. So the change in the freezing temperature equals the constant for the freezing temperature, which once again, unique to each solvent, times molality. And for water, K sub F, there's on 502, there's a bunch of K sub F values. 1.86. Okay. So we have these two different equations. Okay. So let's use them. Okay, let's show you how this works. So this is example problem 6, 503. Sodium chloride, NaCl, we've used that quite a bit, is often used to prevent icy roads and to freeze ice cream. So maybe let's stop and talk about freezing ice cream. If you've ever made ice cream at home, often what you have to do is you pack ice around your mixture. When you add salt, that makes the ice melt. And at first you think, well, why do we want to melt the ice? Because we want to freeze our mixture. Well, in order to melt, it has to pull energy from somewhere. Where does it pull the energy from? Your mixture. And so that's why we can freeze something else by melting ice. Anyway, so what are the boiling and freezing points of a 0.029 molal aqueous solution of sodium chloride? Okay. So now, the hardest part of this is breaking down our sodium chloride, because it tells us we have this molality. Okay? But remember, the whole point of these colligative properties, how many individual particles? So when we look at sodium chloride, it's actually going to break into two different particles. So our molality that we have to put in here, it depends on how many particles. So we take this, multiply by 2. So take whatever your molality is, multiply it by however many particles are in your ionic compound. So this is what we're going to be using in our equations. Okay? And like I said, that is the hardest part of doing this. Because everything else, well, you look up this constant value and you just put it in your calculator. Okay? But you got to remember, multiply by however many particles. Okay? So if, for example, you were using magnesium chloride, okay, this is going to break into 3 different particles. Okay. Sodium hydroxide. Okay. 2 different particles. Okay. So being able to break apart these ionic compounds into however many particles, okay, that is the hardest part. So now we have the molality of the particles. And so, well, we already wrote down our K values. So if you want to change and want to know the change in boiling point, we just go. Okay, so the change in the boiling point is equal to our K value times our molality. Okay. We just put that into our calculator. Okay. So T sub B, the change in T sub B is a whopping 0.03 of a degree. So the new boiling point, so if it asks for the change, that's the change. If it asks for the new boiling point, we have that. We just add it. Okay. So then the boiling point goes up, freezing point goes down. So for this one, take our K sub F. Okay. Put that into our calculator, and it gives us 0.11 of a degree. And now, once again, we change it. We ask for the new one. We start at 0, and we subtract that. So that is the new freezing point. Okay. So if it just asks for the change, that's your answer. If it asks for the new one, you just have to do that. Okay. Like I said, the hardest part is determining how many particles you're going to get from 1 mole. Okay. So. The last thing in the chapter talks about osmosis. Now, osmosis is largely a thing that we talk about in biology. It is basically how water moves across what we call a semi-permeable barrier, basically where water can move across but not everything else. The reason why water can move in and out of our cells, okay, cells in our body, is because, well, there's a difference in concentration of the things that have been dissolved. Okay. Um, Osmosis wants to normalize things, basically make the concentrations the same on both sides. So if you add salt to the outside of the cell, well, that raises the concentration. Okay, now the salt has a really hard time getting across the cell, but water can move really easily. So what it does is water from inside the cell starts moving out, because if you add water, the concentration of salt is going to go down. So that water is going to start moving out of the cell until the concentration of the salts are the same on the inside and the outside. Okay. It's the same thing if somehow you reduce the concentration of the salts. If you reduce the concentration of the salts on the outside, well, now the concentration is higher on the inside, so water starts moving into the cells. Okay. Whatever direction it needs to move, it will move. That's osmosis. It is, like we said, largely something that we talk about in biology, but that's the chemistry behind it. Okay. Just nature likes to have things be as uniform as possible when it can, and that's why osmosis works the way it does. Okay. The force driving it one way or the other is called osmotic pressure, just in case you run into that. So, and that is actually the end of chapter 14. We did it in 2 days because, honestly, because we want to talk about more interesting stuff later on. We're going to rush through a few chapters here so that we can spend more time on some interesting stuff. So, anyway, so we'll stop there. And as always, we do have a little homework assignment, but this one isn't too bad.